Hello, these notes are about end behavior of functions, and more specifically, end behavior asymptotes of rational functions. But first, let's begin by recapping what it means when we talk about end behavior. When we talk about end behavior, we're talking about what the function is doing as x gets larger and larger, or as x approaches infinity. That's talking about the end behavior to the right as x is getting large in this direction. So for this first graph, as x is getting larger, y is really shooting off to infinity. Y is approaching infinity as well. We also can talk about left end behavior as x gets smaller and smaller. As x approaches negative infinity, now that's on the left-hand side, we can see what are the y values doing? Well, they're coming down, they're getting very close to 0. So we can say as x approaches negative infinity, y approaches 0 for our first example graph. Let's look at this one over here. We can talk about end behavior. We can talk about as x approaches infinity, so to the right, what does it look like y is doing? Well, as x gets bigger and bigger, y seems to be leveling out right around that y value of 3. So I'm going to say as x approaches infinity, y approaches 3. And if you notice, the same thing is happening in the other direction. As x approaches negative infinity, y is still approaching 3. Now it's approaching 3 kind of from below, but it still appears to be leveling out. The very last example looks to me kind of like a cubic function, and this one shows that as x is getting really big, y is shooting off to infinity, and as x is approaching negative infinity, y appears to be heading down to negative infinity. Let's write that out. Our right end behavior is as x approaches infinity, y approaches infinity. And on the other side, we can say as x gets smaller and smaller and smaller and smaller, the left end behavior, as x approaches negative infinity, y approaches negative infinity. It's important to understand what end behavior is, because now we're going to investigate it with rational functions. So what is a rational function? A rational function is a function of the form f of x equals p of x over q of x. It's just a fraction, but p of x and q of x are polynomial functions. Those are those nice, smooth functions that we studied a lot in the past, and all we're doing is taking one polynomial divided by another polynomial. And of course, the polynomial on the bottom, q of x, cannot be 0, because then you'd have division by 0 and you'd have an undefined function. Let's take a look at the end behavior, but we're going to think about this. We're going to do a thought experiment instead of actually graphing it. Our first example shows a line divided by a parabola, x plus 5 divided by x squared plus 2x minus 4. Let's think about what happens as x gets really big, as x approaches infinity. Well, let's think about a really large number. How about like 9 billion? On the numerator, we have roughly 9 billion, 9 billion and 5, and on the denominator, we would have 9 billion squared plus 2 times 9 billion minus 4. That 9 billion squared, that really large number squared, is so much bigger than the numerator that when we divide, we essentially have a number that's close to 0. So because the degree of the denominator, x squared, the degree is 2, because it's bigger than that of the numerator, the degree of the numerator is just 1, that denominator grows so much larger than the numerator that when you have a really large number divided into a not so large number, we essentially get 0. As x approaches infinity, y is approaching 0. The same thing happens in the other direction. As x approaches negative infinity, y approaches 0. Because we have that same end behavior on either side, we can actually talk about a horizontal asymptote, or an end behavior asymptote. Our end behavior asymptote ends up being horizontal. It's a horizontal line, and the equation for that line is y equals 0, because on both ends our function was approaching 0. And again, the reason for that is when x is really big, you have kind of a small number divided by a huge number, and that's essentially equal to 0. Think about it. You have one cookie divided among 9 billion of your friends. Everyone's going to get like less than a crumb. So pretty much 0 cookies. Let's take this idea and investigate it with this rational function. This time we have a cubic over a quintic. But the same thing happens because the quintic is on the denominator. We can see that the degree, x to the 5th is telling us our degree. Our degree is 5. Our degree of our denominator is larger than the degree of the numerator. That means that when you plug in really large numbers, as x is approaching infinity, you're going to get a pretty big number over a really, 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 really big number. We have the same behavior as before. Y is going to approach 0. As x gets larger and larger and larger, our function is pretty much shrinking to 0. Again, we have that idea where the degree of the denominator being larger makes us divide by these really huge numbers when x is big, and we essentially get very small y values. The same thing happens on the other end. As x approaches negative infinity, y is approaching 0. So our end behavior asymptote, this time I'm going to abbreviate it EBA, our end behavior asymptote is again that horizontal line, y equals 0. In general, we can talk about finding our EBA by investigating the degrees of the numerator and the denominator. When the degree of the denominator is larger, our EBA is always y equals 0 for these rational functions. But what about when the degrees are equal? In g of x, we have 3x minus 7 over 8x plus 1. The degree of the top is 1. The degree of the bottom is 1. Remember, degree is the highest exponent of our polynomial. They're both linear, they both have degrees equal to 1. If we think about as x gets larger and larger, well, what's happening? Imagine that you have a really, really large bank account. When x is getting huge, 3x minus 7, you're not going to notice those minus $7. You're not going to notice if somebody takes $7 away from your account that has $9 billion in it. So that means as x is getting bigger and bigger and bigger, our function g of x pretty much looks like the function 3x over 8x. Right? In our denominator, as x is getting huge, the 8x kind of takes over. Who cares about adding $1 when you already have $9 billion in your account? So because of that behavior, we can actually notice that at the ends, our function is looking like the ratio 3/8. We keep that ratio, 3x over 8x, when x is huge, because the minus 7 and the plus 1 don't really come into play. They don't really matter as much. That is our EBA. So, if we have the degrees that are the same, we actually only need to look at these lead coefficients, 3 over 8. So I can actually say our EBA, our end behavior asymptote, is again a horizontal line, and the equation for that horizontal line is y equals 3/8 for that first one. The degree of the top was the same as the degree of the bottom, so we just look at the lead coefficient ratios. Same thing applies for h of x. What do you think the EBA is going to be? Well, if you said 1/2, you're correct. Let's figure out why. The degree of the numerator is 2. The degree of the denominator is 2. That's the same. So I know that the ratio holds when x is getting really, really large. If that ratio holds, I only need to look at the ratio of the lead coefficients, 5/10. It's a horizontal line, y equals 5/10. Oh, but I can just reduce that fraction. Y equals 1/2. There's our EBA. You might be asking yourself, what the heck happened to that 17x, and what the heck happened to the 4? When you're talking about the end behavior, the very ends of the graph, that's when x is really, 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 really positive, or very, 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 very negative. Huge numbers we're talking about. The 17x, the negative 17x, and the positive 4 simply become less important at the ends. The expressions or the terms involving the highest degree those kind of take over when we're at the ends of the graph. Okay, so we talked about what happens when the degree of the denominator is bigger. We talked about what happened when the degrees of the numerator and the denominator were the same. What happens when the degree of the numerator is bigger? There still could be an end behavior asymptote. It is not horizontal. You'll learn a lot about what to do when the degree of the numerator is bigger next year when you take advanced math. But for now, we can just say there might be an EBA, there might be an end behavior asymptote, but all we need to note right now is that the end behavior asymptote for these cases is not horizontal. So there is some end behavior that is interesting to talk about, but all we need to know is that it's not a horizontal line. Let's summarize. Here's where we can write down all of the stuff that we talked about, nice and concise. If the degree of the denominator is larger, so again we're dealing with this rational function p of x over q of x, then the end behavior asymptote is a horizontal line, and it's always y equals 0. That's my favorite case, because I just have to look at the degrees. If the degree of the denominator is larger, y equals 0. Done. If the degree of the numerator and the denominator are the same, then, again, we have a horizontal asymptote, and it's going to be the ratio of the lead coefficients, also a horizontal line. If the degree of the numerator is larger, then you'll investigate that a lot more later on. But for right now, we can just say that the EBA, the end behavior asymptote, is not a horizontal line. For now, this summary for rational functions should be enough to get you started. We want to investigate the degrees. That's the highest exponent in our polynomials. And if we can tell which case it falls into, then we definitely know something about the end behavior asymptote. Have fun!